Okay, so now what we will be considering is our major problem statement. There are many people and those are being simulated. So let's take in a simple scenario. This represents the corridor just ahead of me. It's a big one. We are a rich university, and this is probably me who is trying to get out. Maybe I want to meet someone. Maybe I'm just fed up, want to go home. And let's say this is the guy who sits down here who is also doing the same thing. And of course, we two are obstacles to each other. As you can see, this man is actually a little bit down, so and I'm a little bit up, so soon we'll start to develop a repulsion. It'll be a little bit on the positive y-axis for me and the negative y-axis for this guy, and our trajectories will dent like this little bit. And then what happens is in y-axis I still have a positive force, and in y-axis this person has a negative force. The boundaries I'm assuming don't apply any force, so to make it wide, let's just delete them up. So I go a little bit more over here, and then I go a little bit more over here, and then of course we travel as usual. Now, if you've seen the two of us moving around, surprise, that's not how we move. I go here, and this person goes here. We just exchange hello, hi, how are you doing? What do we do to make lives of robotic students terrible? So we just give a glance and we go by. So we live in some distance around over here, and there's something special about this distance. It's socialistic in nature. So if you leave it for a typical potential field modeling, it will simulate something that we both hate each other and we just don't like each other. So we're just going away from each other. So we live a very large distance. When in reality, this is a kind of affection that we show. In order to do this, I say that unlike static obstacles, people attract each other. I think I need to say that when coming outside classes, you see your friends, you get attracted to them. You meet your friend, you form a group, you get attracted to them. You see a girl from your batch passing by, you just feel a bit of an attraction. You don't go far away because of a repulsion. But then if people want to attract each other, they would end up like this, and that's bad. Too much of personal space, so they also repel each other. And if what I say is that every person likes a nice socialistic distance, the sock, and people attract each other if the distance between them is greater than the sock, and people repel each other if the distance between them is less than equal to the sock. At the sock, attraction and repulsion cancel each other. So let me intuitively give that up. So the same two people That's me, that's my colleague. The distance is too large, so we'll attract each other. That's me and that's my colleague. And if our wives come to know about this, it'll be very bad for us, so we'll repel each other. And that's me. And this is the person next by. If we are at the sock, we nicely go along. Whether it be this direction or that direction, we go upon nicely. No attraction or repulsion from each other. We are at an equilibrium. On the other hand, if you break this equilibrium by keeping us apart or close by, we'll attain that equilibrium again. If we are walking in the same direction, opposite, nothing can happen. Now, it turns out that this equilibrium distance is actually a function of the two people as well. So there are two people here. This is my research scholar and say this is this person's research scholar, and they are more pleasing to each other, so they do keep a distance which is pretty small as compared to ours. So research scholar RK, research scholar, this guy is less than the sock. So it's a function of the two people. And it depends upon the acquaintance level. So if you are friends, you go close to each other. That too, if you are undergraduate friends, you really go close to each other. If you are postgraduate, you are still further apart. Research scholar, you go apart. If you are both boys and friends, you go pretty close by. If you are boy and girl, you go even more close by. If you are two girls, you probably maintain a lot of distance from each other. So it's a function of who the two people are. It's also based on acquaintance level. So if you are close friends, you are close by. If you don't know each other, you are far apart. If you're enemies, you are very far apart. So this is what will happen if it's me and it is my research scholar who did not do work. Very large distance. And that's what's special about this force between two people. It could be attractive, it could be repulsive, and whether it's attractive or it's repulsive, it depends upon who the two people are. So we model it in the most generalized say. We say the repulsion force or the attractive force between person Q1 and Q2 is equal to K, which is associated with a degree associated with Q1 and Q2 simultaneously. So this is based on the affinity level. The value of K that you actually select is based on the affinity level. So it's just saying that it's not K to the power, it is K to the particular person. So let me put it as a subscript. So K, which is specific to the two or people involved. And of course, it will be 1 upon distance between Q1 and Q2 raised to the power sigma, which is also particular between Q1 and Q2. We both may have it squared, some other two people will have it cubed, some other two people will have it raised to power 2.5. And this is the unit vector. Now, attraction was in general directly proportional. Here we have made it inverse, because if you are here and your friend is here, it's not that you'll go running to your friend. You are doing your own business. So if you're close by, then only you actually attract. If you're far away, then you don't care about each other. Who will walk that much amount of an extra mile to cover up the distance? So I kept it as inversely proportional to the distance around over here. Now, what really happens is that at equilibrium, which is at d sock specific to Q1 and Q2, F attraction between Q1 Q2 should be equal to F repulsion between Q1 and Q2. And when I say the attraction force and the repulsion forces are opposite, then is when I say that the two forces are, the two people are pretty much equal and opposite to each other. And you put in this equation around over here, and you put in a similar equation around over here. This will be different for the case of attraction and repulsion, and this will also be different for the case of attraction and repulsion. So you get constraints between attraction and repulsion such that the equidistance forces are there at the equilibrium point. So all that we have to do is that we need to say that every two people attract each other and repel each other. The characteristic profile by which they attract and repel, I did not speak anything about that. It is characteristic to the two people. The attraction force, it dominates when the two people are far apart, and the repulsion force dominates if the two people are close by. So this is at the sock. So if distance between Q1 and Q2 is greater than the sock, then you have attraction applies, and if distance between Q1 and Q2 is less than the sock, then you've got a repulsion which applies. So at socialistic distance, no force, greater you have attraction and lesser you have repulsion. And that's how you model the force. If you want to say that two people are friends, then the attraction coefficient will be larger for no acquaintance will be smaller, and similarly for the repulsion. So friends mostly attract each other even at small distance, and they only repel each other when they are very close by. If you have no acquaintance, you'll start repelling very early, so repulsion is higher and your attraction is small. Similarly, you can control sigma as well. Similarly, you can control the degree as well, keeping the actual profile constants. Now, there's another way by which the same force can be modeled, and there's one natural entity that has exactly the same effect. So that's Q1 and that's Q2, and that's called as a spring. So a spring has a natural length of d sock. If you make the people too close to each other, then the spring exerts a force, K again, which is typical to Q1 and Q2. Its natural length minus the current distance, and it's repulsive in nature. And if you have the two which are far away from each other, then again the same thing with a negative sign, so then this becomes negative in nature. and the forces are attractive in nature. So that's another way you can model exactly the same effect, that the two friends are connected by a spring that controls how much they contract and how much they expand to each other. Now, luckily, you don't need to specify all the parameters for every person. So this would mean what? K attraction, n square parameters for n people depending upon their affinity level, and sigma again n square parameters for n people depending upon their affinity level. You don't need to do that, because you can always say that people are classified as groups. And in your batch, you know who are the friends, who are very close to each other, who are just okay friends, and who are enemies. So we say all people are basically into groups. Every person belongs to one or the other groups, and when you say K attraction between Q1 and Q2, it's a function of K attraction between group to which the person belongs to and group to which person 2 belongs to. So rather than modeling attraction forces between every people, you model them between every group. You look at the group and then you say, okay, these two groups, they love each other, so there'll be strong attraction. These two groups, they hate each other, so there'll be a stronger repulsion, weaker attraction. That's how the groups behave. What you can do is, you can even take this up easier to model. You can say that people, of course, belong to group so you can say that people are strongly attracted to their own group and weakly attracted to other groups. That means you have intragroup attraction and repulsion coefficients, and you have intergroup attraction and repulsion coefficients only. And that's more practical. So let me take an examples. I go to the market, families, one group of friends, one group, couples, another group, two people dating each other, another group, a lonely person like me, also one group. One person can make a group. And you see that the two groups don't let each other come in, and together they are very strong with each other. So that's you only need to model intra-group forces which are more attractive, less repulsive, and intergroup forces which are more repulsive and least attractive. And that's we're not taking the boundary line cases, because here also a person could be a member of both the groups, and that's what you see when returning from classes. The person goes with you as friends and suddenly sees his girl and suddenly is a member of both the groups, feels both the attraction. Where does the person go? Towards the girl, towards the group, towards the girl, towards the group. So people could have multiple membership. The membership could be fuzzy. I casually hang around with you people. I don't often hang around, so given a chance, I might just sneak out. I don't feel that much attraction, so in your group, you might see me as an outlier. I have a weak membership, I've got a weak force. To make it simple, let's not take membership and let's not take in multiple groups. Similarly, here, multiple groups, when you say that they are intra-group and they are intra and inter-group attraction and repulsion coefficients, you as friends went together, watched a movie, are into this movie theater, and guess what? Another seniors group of yours is there, you'll still feel a stronger attraction. A faculty group comes in, you both the groups will be repelling because you just got an assignment extended because you were busy, now you need to hide, so there's a strong repulsion. So, not modeling for such cases, we just say that to make simulation simple, we say everything is intergroup and everything is intragroup. So there are intergroup attraction and repulsion forces, and there are intragroup attraction and repulsion forces.